and then the song ends. That works too. Hi, everybody. We're going to be doing Chapter 7 today, or Unit 7. I got to start calling them units. Which is an exploration of the nature of matter. The atomic nature, I should be more specific. Although we're going to try and talk a little bit about other arrangements of atoms that exist too. I didn't get my tablet out, so let me just do that really quick. I see everyone's talking about Among Us. I wish I could play it with everybody, but that's sort of a conflict of interest. Haha! The instructor's playing. Let's make sure he gets killed first. And then that wouldn't be very fun for me. But I seriously want to play it. It sounds amazing. Where is my slide? Oh, I gotta click over here first. I couldn't find my PowerPoint over here. What are we doing other than just atoms? Oh, we're going to talk about ions. Ions are really important in chemistry because they are abundant and all around us and have interesting chemical and physical properties. So it's going to be very important that we understand how ionic matter forms and how it interacts with other matter. That's going to bring up the concept of charge. Charge is this nebulous thing that people have definitely heard of because you know positive and negative charges and electricity and batteries and things like that. But what exactly does that mean for atoms and stuff like that? We're going to explore some of those topics in this chapter. So that's the premise behind Unit 7. So I don't think that there were any other questions in the chat other than like Among Us stuff and then the lab number 1. Yeah, I'm working on lab number 1. I'm trying to grade them when I can. I have half of them done. I didn't get much time to do it last night because I had to host a stream for a bunch of friends that play video games really fast. And I hope to have the grading done. I can do some of it tonight and some of it tomorrow, so hopefully Friday, but if not Friday, then Saturday. And so, yeah, most people are doing really well. I think the only problem that's coming up on lab number 1 is people leaving tables blank either inadvertently or on purpose. And if you leave a blank, I have to not give you credit for it. But let me get back to your question when we get to the break. So hold on to that and then remind me because we'll go over that at that time, just because I'm in the middle of the lecture, I guess. So we're going to talk about atoms today. What is an atom conceptually? So you might have this idea of what an atom is, but what exactly is it? So let's say that you had a block of copper, or a sheet of copper, some like chunk. Here's my copper. It's blue, because blue is easy to see the word copper on it. And what I'm going to do is I'm going to cut this piece in half. Boop, there we go. And then what I'm going to do is I'm going to cut it in half again. Boop. And then I'm going to do it again and again and again and again. Boop, 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 boop. At some point, I will get down to the tiniest piece of matter that is possible. Boop. That. And that tiniest piece is what we're going to call an atom. Now, this is sort of a conceptual thing, because when this idea was pitched, and this idea was pitched by a Greek philosopher named Democritus, a very, very long time ago, he did not possess any sort of method or technology to allow him to look down at the atomic level. And I'm going to show you a picture of some atoms, I believe, on a slide coming up. But he thought about this just conceptually. There must be some smallest piece of this copper, he said, that if you try and split it in half, what you end up with is no longer copper. In fact, if you were to cut copper in half, you would end up with, I gotta look at the periodic table here to see this, you'd end up with silicon and phosphorus. And how the heck do you know that? Well, what we're going to study today are the parts of the atom, and not necessarily like how we discover these. That'll be covered in 161. But just what the parts are. Okay. So the atom is just the smallest, teeniest, tiniest piece of matter that represents one of the elements on the periodic table. Now, on the right, you can see what looks kind of like this honeycomb that looks really blurry. Each of those dots is a gold atom. And what the gold atoms do is they arrange themselves in solids in a regular way, like we saw in my diagram on Tuesday. And they basically just sit there. Or they vibrate, or maybe they move around if they're a liquid or whatever. Now, because these atoms are so small, you need absolute huge quantities of them to even be able to see them. Have I seen the quarters video on the size of an atom? I bet I have, but I can't think of it or remember it at this moment. But it's extremely small. You have to zoom in forever to get to the size of the atom. And even that atom that you're seeing, that's the electron cloud. So you're not actually seeing the nucleus. You're not seeing the solid part of it. You're just seeing the thing buzzing around that absorbs light and reflects it back at you. We're going to talk about that. That's going to be part of today's discussion. Oh, we're going to talk about it right here. Here's the nucleus in an atom. Boop. It's this little red circle floating around in the middle of nowhere. The diameter of a nucleus is roughly 10 to the minus 15 meters. Notice that there's only one sig fig because that's all we can really get. Yep, that checks out. A penny made of atoms the size of a tennis ball would be larger than the observable universe. I believe that. That doesn't surprise me at all. Because atoms are just so small. I can't even imagine 10 to the minus 15 meters. Like, the smallest gap that I can imagine, and then divide that by another quintillion. Now, the thing that you saw on the picture, the round circle there, boop, that was called the electron cloud. The electron cloud is where electrons live, but is more or less just empty. The solid part of the atom is the nucleus in the center. Oops, I didn't mean to do that. So this part is solid, but this part is just a void. So what that means is that all matter that is, by definition, atomic is mostly just empty space. So if somebody calls you an airhead, you should say, yeah, that's true. That checks out. Although, not technically an airhead, because there isn't any air in the void between all of your atoms. So you are mostly just empty space. There's a lot of emo jokes that can go with this. I'll leave those as an exercise to the viewer to come up with. But the only part of the atom that is solid and physical is the nucleus, and then the electrons buzzing around in that cloud, which are super teeny tiny as well. Alright, what lives in the nucleus? We're going to talk about that and show how that is the important part of what chemistry is and how we identify stuff. But for now, what we're going to concede is that there's something in the nucleus, and that determines what the atom is. And there are 118 known configurations, and in fact, there are actually a lot more. But there are 118 known different atoms that we have put on the periodic table and that we have observed. Now, when you take any of the atoms on the periodic table and you expose them to certain conditions, such as like, oh, I heat them in the presence of oxygen, or I expose them to chlorine gas, then the result that you get is always the same, regardless of any individual discrepancies within the atoms in terms of like their mass and stuff. So we'll talk about isotopes later. But any atoms that have the same identity will react the same way. So what that means is if you take sodium atom A and sodium atom B and you put sodium atom A in water, sodium B will react exactly the same way, which is boom, it'll explode. All sodium behaves exactly the same under the same conditions. All copper behaves exactly the same under the same conditions. But sodium and copper react differently, which allows us to differentiate them, as you saw in experiment 1. Now, why does this happen? What's the theory behind how chemicals react and interact with each other? That's the whole point of this class and of 161 through 163. So we're going to study that in great detail in the coming quarters. Now, what happens if you put atoms together? When you bond atoms together in some means, and we're going to spend chapters, I want to say it's 9 and 10 on bonding, then what you end up getting is called a compound. So we've already seen the word compound in chapter 6. That was how we categorized matter. One form of matter was an element if it was pure, and the other form was a compound. Different arrangements of molecules, different arrangements of atoms to form molecules will create unique results. For instance, there are many possibilities that you can get when you combine hydrogen and oxygen. One's H2O, one's hydrogen peroxide, you get a hydroxide, and all three of those are different. Water is very, very, very electrically neutral. It's very stable. It's polar. It's not very reactive with most things. Peroxide, on the other hand, if you spill it in your sink, it starts to bubble and fizz because it's immediately reacting. And that's the 2% or 3% stuff you buy at the store. If you've had 30% or, heaven forbid, 100% peroxide, like, that stuff it's like almost explosive how dangerous it is. I've worked with 30% peroxide for an experimental demo that we do in the spring for 5th graders, and holy crap does that stuff get hot. Like, you pour it in the container and then just foom, it goes everywhere. Yeah, I do Elephant's toothpaste. That's the one I do. I do that for a bunch of 5th graders. I forget what the high school is that's next to Everett Community College. But in the spring, we invite a bunch of people over, and I do the elephant toothpaste experiment, and then a bunch of our other departments do science. It's the science fair and student exposition that we do every year, although we're not doing it this year for obvious reasons, and we had to cancel it last year because COVID. So, but anyway, that's water, peroxide, very different, and the difference is they have different chemical formulas, which arises from them having different chemical arrangements due to having different atoms in them. So atoms can be unique from each other, and molecules can be unique from each other too. In fact, what you'll learn in 161 is two chemicals with the same formula could have a different structure and do very different things. And I always forget this example, but there is an isomer or stereoisomer of some chemical compound. Like, one form of it is a birth control, and the other form of it causes deformation in children when they're born. And they're the same chemical formula, but it's just like one molecule has an atom that's just bloop, it points in a different direction. And suddenly that causes like 40% chance of birth defects. So this rule on the board here that each combination gives a unique identity is not the complete picture. Like, you can have the same formula, and then there's still nuance to that too. So there's a lot to talk about and unpack here, is the takeaway. Now, what is chemistry? Well, chemistry is the interaction between matter and other forms of matter and the observations of what happens afterward. When you do chemistry, what you are doing at the atomic level is rearranging atoms so that they form new substances. You can either make a new compound, maybe you break apart atoms that are in a compound so you just get elements by themselves. Maybe you swap one out for the other. You can do all sorts of possible things. And so what our job is to figure out how those reactions happen. Now, a caveat of this is that when we are doing chemistry, we have to assume that atoms are indestructible. Now, the reasons for that are pretty pragmatic. If you put a bunch of atoms in a container, whether they're solid, liquid, or gas or whatever. Let's assume that they're gas, because gas particles would be moving the fastest. Their velocity with each other is not high enough that if they bump into each other, they would shatter. So if I have two oxygen atoms that are flying around in a container and they collide into each other at hundreds of meters per second velocities, they're just going to go bonk and bounce off of each other, and they won't explode into tons and tons and tons of pieces. If they did do that, and it is possible to heat things up to the point where they do that, this is what happens in the sun, you get interesting effects, and this is called nuclear chemistry. So if atoms do get destroyed, and by destroyed, what I really mean is they get combined into bigger atoms or they disintegrate into smaller atoms, that's called nuclear chemistry. We're not going to talk about nuclear chemistry in this class, unfortunately, because one, it's complex, and two, it's super interesting, and we kind of want you to take all of the chem series. So we put it at the end. That's how we get you. But for the purposes of chemistry, you put an atom in, you get an atom out. Every atom of aluminum that you put into your reaction container will come out, because that's the conservation of mass in action, right? If I put in 3,000 oxygen atoms and 2,000 aluminum atoms, I'm going to get them all out, but they might be bonded together in some other way now when the reaction is done. Now, we're going to talk about these types of compounds a lot more later on. In fact, Chapter 9 is entirely ionic compounds, and Chapter 10 is entirely molecular compounds. But what we want to do at the onset is we want to establish a distinction between two different types of common compounds that we're going to encounter. The first one I want to talk about is molecular, and what I'm going to do, that's not a good color. Let's do this. There we go. You can see that I'm circling my molecules here. And that when I do so, the line that I'm drawing does not pass through any atoms. There's a space between all of my molecules. And I don't want to draw that one in white because I'm going to draw over hydrogen. So let me do this. So space. There's a space or a gap between all the molecules. So what that means is that each of these things that I've circled is independent. Molecules are independent. They bounce around on their own, and if they bump into each other, they can do interesting things. So maybe like make another interaction or a new molecule or whatever. Or they just bounce off and they go on their merry way. Is diamond ionic? Diamond is actually a molecular compound. More specifically, it's called a covalent network solid. Just because it's only carbon. Do we talk about that later? Maybe in chapter 10, we'll talk about diamond. Diamond's a really common one, though. Now, what's the opposite of this? Or, not really opposite. We should just say that this is just the other thing that we observe. Right here, I'm going to circle a pair of sodium and chlorine. And what you'll notice about, say, this chlorine here is that it touches each of its neighbors directly. So that chlorine atom, the green sphere, is stuck to all of its neighbors, and they're stuck together for a specific reason. The reason being that these atoms are actually charged ions, as you can see here, with these symbols that we've put down. We haven't really talked about charge yet, but suffice it to say that there's actually a force that holds all of these things together with their neighbors. And all of those things get coalesced into what's known as a lattice. So this block of repeating, alternating atoms is called a lattice. That's what this is. And so you don't actually see a molecule in an ionic compound. You just see this repeating array of whatever atoms are used in the ionic compound. Those are the two types of structures we're going to deal with in this class, and for most of the 160 series. Molecules, which are independent entities of bonded atoms, and then ionic compounds, which are different ions that are all attracted to each other and just sort of stuck in a solid. On this slide, we're going to explore the idea of a molecule in a little bit more detail. Most matter is molecular. It's not common for atoms to just fly around individually unless they're noble gases. So, for instance, helium, neon, argon, krypton, and xenon, and radon, they all exist as independent atoms. They just bounce around on their own. But nearly all other gases and all other matter in general exists as what is a molecule. I got a bunch of pictures on the board here. Now, what you can see here is that my hydrogen atoms, which are these white spheres, are sort of superimposed on each other, where I'm going to paint the yellow right there. I can do that with the hydrogen, or the oxygen. It doesn't really show up as well there. In the region where their spherical orbitals overlap, that's where bonding occurs. We're going to talk about bonding in, again, 9 and 10. Now, these are all examples of molecules because they contain more than one atom. So atomic matter would just be individual atoms by themselves up here. We're going to call this atomic. But all of this down here is molecular. And the atoms can be the same or they can be different. So we got water, CO2, and sugar on the right. And we got some elemental matter on the left here. Now, to go back to what we were categorizing from before, these guys would be elements. Even though there are more than one atom involved, they're all the same atom within their molecule. These over here would be compounds. Alright, how we all doing? That sound good? I gotta take another drink of water. Alright, we're going to throw out some terms here. These terms are going to be used to describe molecules. The first term that we're going to look at is a number term. And so we're going to use numeric prefixes, mono, di, tri, tetra, etc. to describe how many atoms are present in the molecule that we're looking at. Now, the reason that we actually have these terms monatomic, diatomic, and triatomic is because there are enough molecules out there that have 1, 2, or 3 atoms that it's worth using. Beyond 3, we use polyatomic. If you wanted to be more specific, you could use a numeric prefix for those numbers. So you could say something was tetratomic because it had 4 atoms in it. But at that point, there are just so many possibilities that you can pick from that it just makes sense to say polyatomic. So those are the 4 terms that are highlighted that you really need to know. Monatomic, diatomic, triatomic, polyatomic. And what that means is 1 atom, 2 atoms, 3 atoms, or more than 3 atoms. So that's the first term that we have to assign to molecules. The second term is going to be type. And then that's going to describe how many different types of atoms are present in the molecule. Is it all one type of atom, or are there different types of atoms? So if they're all the same type of atom, like the molecule on the left, that's oxygen, O2, we're going to call it homoatomic, because homo means same. If there are different types of atoms, we're going to call it heteroatomic, because hetero means different. Now, you can apply a number label. Oh, I should highlight these too, because these are terms that you want to know. You're going to apply a number label and a type label to molecules. So you would call something, say, heteroatomic and diatomic. That would mean something that has two different atoms in this molecule. Or you could say homoatomic and triatomic. That would mean you have a 3-atom molecule and all of the atoms are identical. Those are just different things that you can use to describe. So what I'm going to have you do is I'm going to have you do that on this slide here. So here are 6 different molecules. I had to put these lines here because people kept linking up the pictures with the formulas. The pictures and the formulas are not linked in any way. They're just 6 different examples. So give each a number term and a type term. So the first one has 3 red atoms. What 2 terms would you call it? Put those answers in the chat, and we'll go over the answers together in just a bit. Assume that all of these are molecules, even though some of them aren't. All right, let's go over the answers here. Where is... Oh, there's my stylus. So what we're going to do... Let's count how many atoms there are. That's not the pen. That is the highlighter. There we go. So there's 3 atoms here. So the correct term that I would use for this is triatomic. And then they are all the same type. They're all red atoms, whatever red represents. So I'm going to call it homoatomic. There you go. For this second one, I have 5 different atoms. That's more than 3, so we'll say polyatomic. Now, one of them's blue, the rest are red, so that means there are different types. There you go. Over here, I have a green atom with like a weird blue border because I guess when I made this slide 75 years ago, I didn't know how to Photoshop very well. So there's only one atom here, so it's monoatomic. Ah, my C kind of got stuck there. There we go. Monatomic. I shouldn't actually add that extra O in there. Now, monatomic and homoatomic kind of go hand in hand. Like, if you're monatomic, you can't be anything but homoatomic. Now that we have formulas, we're not going to deal with pictures anymore, but turning the formula into a picture in your head isn't that difficult. So you could say, oh, I have 6 of these C's and 6 of these H's. Those are different, so we know that this is heteroatomic. There are no ghosts in the closet. Why are you like this? Stop that. My cat is just yowling at the closet. I don't even know where I was. Polyatomic, that's right. He just loves to jump in the closet on top of this box, point up at the top corner of it, and then cry at the top of his lungs. Ghosts! I found them! They're inside here. What is this? This is diatomic, because there's 2. And also homoatomic, because they're both bromine. This one over here, we're going to call it triatomic, assuming that it is... Oops. Molecular, it's not. It's actually ionic, but that's okay. Gosh, don't get me started on that whatever ghost game that's come out. The one where it's like a group of friends ghost hunting. That's freaking creepy, and I don't like playing horror games. I like watching them. Phasmophobia, that's it. Yeah, I've watched a few people play that, and I'm just like, nope, that is not a game I will play. Where are we for time? Let's see here. It's a little early for the break, so we'll keep going. Alright, so those are our categorization terms. You're going to need to apply a number term and a type term to different molecules presented to you. Oh, no, don't play it in VR. Don't do that. Why? That's such a great idea, and just no. That's not what I want to do. Alright, here's our atom zoomed in, so you get a better look at it now. Is it a VR game? Oh, I thought you played with a keyboard and mouse. Oh, well, anyway. Now, this picture is a little exaggerated. Remember how the nucleus was 10 to the 15, and the electron cloud was 10 to the minus 10. So, in reality, here's my nucleus, this little dot that I drew right here, and then here's the electron cloud, like, way over here. It's so big. So this picture is obviously exaggerated. So just keep that in mind here. But all of the matter in the atom is going to be found primarily in the nucleus. The nucleus contains two different particles that you can see here. We're going to talk about these particles in just a second. But the electron cloud is where all the electrons are. Now, this note down here, that remember that this is exaggerated. If I had the carbon atom shown with that size nucleus, its electron cloud would extend all the way to Fred Meyer, which is like 5 miles away from me. And yeah, that is where the electrons are expected to be. They could, in theory, be anywhere, because electrons are traveling so quickly that measurement becomes nearly impossible to determine. Now, the things that are in the nucleus are called nucleons. In the slides, I try to adapt the same color for all of them so that protons are written in blue and neutrons are written in red. Later on, like when we talk about charge, that kind of breaks down a little bit. But just to match up with the pieces that you see here. Here are our protons. Now that I've drawn the yellow over them, they're no longer blue and red. So let me not do that. Oops. But the nucleons live in the nucleus being the center of the atom. The electrons are on the outside. Electrons cannot go into the nucleus. If they do, they would combine with protons and you'd get a nuclear reaction. Now, there are reasons why this doesn't happen on its own. And when we talk about charge, we'll talk about how charge functions and what the atoms are doing to prevent the atoms from just collapsing. Any two charges that are alike cause the effect of repulsion. So if I have a positive and a positive charge, and I try and put them next to each other, what ends up happening is this. They repel. The same is true as if they were negative. So these two charges would also nope on out. So if you have two of the same charge, they yeet each other. They separate apart. Now, if you have the same charge, or not, I'm sorry, not the same charge. If you have opposite charges, and there's only one combination of this, then what ends up happening is that instead of pushing each other apart, they come together. And they'll stick. Now, you can immediately see a problem with how my atom is displayed, right? These protons should fly apart, and these electrons should get drawn to the nucleus, right? So how the heck is all of this arrangement going on? Well, electrostatic forces are not the complete picture. There's actually another force that holds the nucleus of an atom together. And this is called the nuclear force. Specifically, the strong nuclear force is what occurs from when neutrons are next to protons. Neutrons hold protons together. You can think of a neutron like nuclear glue. So there is a reason why there are neutrons in the center, and that reason is to prevent all the protons from just repelling apart from each other and then all of matter annihilated. Alright. Now, in an atom, the observation that we make is that the atom is electrically neutral. What that means is that the number of protons and the number of electrons in any atom are the same. I'm going to highlight this word in a different color because that's the key word here. In an atom. Okay? Later on, we're going to define what an ion is. Ions do not have the same number of protons and electrons. So it's very important that you are looking at the lingo for problems in Chapter 7, because I might say, determine the number of electrons on this atom. And if I say the word atom, then what that means is, oh, I have the same number of electrons as protons. So if you know what its identity is, you know how many electrons it has. But if I say ion, then the number of electrons and protons can be different. Okay? So make sure you differentiate between these two terms when you're doing your review for the quiz. Now, how easy is it to remove atoms or add atoms? Turns out that it's not that hard because, remember, again, this electron is really far away from the nucleus. It's attracted to the nucleus, but it's very distant. So, if we wanted to, we could either remove it, or we could add another one in there. And it shouldn't be that difficult to do because these guys are very mobile. The mobility of electrons leads to electricity, which is something that we use right now, obviously. You're using electricity to stream this presentation. So electrons are going to be very relevant to us because this is the mechanism in which we use to generate power and power things. And so understanding that concept of matter is useful and interesting. Now, the last little bit about identifying the parts of an atom comes down to how do we figure out what atom is what? And the definition that we have selected when we as a society came up with all of this, or a civilization, I should say, is called the atomic number. The atomic number is the number of protons an atom has. So if you pick up an atom, like, assume that you could do that, and the atom has 6 protons in it, it must be carbon, by definition. On the periodic table, the atomic number is written as an integer, and it's usually placed in either the top or the top corner. On the Web Elements periodic table that I have, it's the top number centered over the symbol. But I think on the p-table on the p-table table that I recommended, I think it's in the top left, but I'm not 100% sure. That number is the number of protons something has. And so that's our identifier. We just decided, okay, if you've got 1 proton, you're hydrogen. If you've got 2, it's helium. 3, it's lithium, and so on and so forth. All the way up to 118. And because those components in the center are discrete, and we can't break them apart using chemistry, you can using physics with particle accelerators and stuff. But in a chemical reaction, those pieces stay whole, and you won't ever have a fraction of a proton. So there's only 118 possibilities so far. We're going to do isotopic notation, I think, after the break. So I'm going to pause here. Let's put the sample... Oops, not the sample problem viewer. We'll put the break time logo up there. Where'd my timer go? There we go. Let me scroll this out of the way. Close this menu box. And I gotta find... There we go. Okay. So let me start the timer here. And we'll play some more Final Fantasy VII music for you guys over the break. See you in a bit. Oh no, I ran out of music for the last 15 seconds, so we'll just sit here in silence, I guess. Oh, I broke the timer. Never mind. Whatever. Yeah, I love everything about Final Fantasy VII Remake. Like, it's so good. I was very, very concerned when I heard that they were remaking the game and they were doing things to my precious baby, which is Final Fantasy VII. And, because I played it in '97 when it came out, and I grew up with that game, and like it's very, very important to me. And I started to see the stuff that was coming out, and I was like, okay, this is not bad. And then I played the game, and I was like, wow, I don't know what a perfect game would be, but I would very happily put this right beneath that. Like, it. I've never played a game that like consumed me so much as that game. And I realized that like 50% of that like enjoyment was nostalgia because everything about it was nostalgic. But it's just amazing. And if you were born before 1990 and you got to play it, you should definitely play it. And if you weren't, you should still play it anyway. What are we doing? We're doing isotopic notation symbols. Okay, so we're going to define some terms here. We've already defined the atomic number, which is just the number of protons. I'm going to assign that a variable. The variable we use for this is called Z. Z is the number of protons an atom has, so it's just going to be related to its identity. We're going to then... Oops, we're not going to do that. We're going to then define a new variable A, which is called the mass number. The mass number is how many protons there are and how many neutrons there are. Those numbers added together. Now, that might seem kind of silly, because, well, wait a second, didn't we just do this up here? Why do I have to do it again? But this is just the convention that we have selected. So, now, again, here comes that terminology that we just talked about before the break. In an atom, the number of protons and the number of electrons are the same. So if you know the atomic number, you also know the electron total for a neutral atom. For ions, it's different. We'll talk about that in... We'll probably get to it today. We'll do a little bit of that on Tuesday as well. Now, there is a number on the periodic table. It looks like a decimal. I don't know how many of you have periodic tables open, but you probably will want it for the rest of the lesson and probably for the rest of the quarter. Just have it handy. There is a number on the bottom of the periodic table that looks like a fractional decimal sort of thing. Sometimes they round really close to a whole number. Most of the times they don't. That number is not the number that we're talking about right now for the mass number, okay? That is a different mass on the periodic table. So the mass number is not shown on the periodic table. So the mass number A is its own specific thing. What we're going to do with Z and A is we're going to assign them to figure out the identity of a given atom. And we're going to do this on an atom-by-atom basis. Okay? And so we'll do that on this slide. Here's what we're going to do. On the board, I have curly bracket E. I'm going to delete that notation and replace it with the correct symbol that I'm looking at. I'm just using curly bracket E as a placeholder. Okay, so in this space, you're going to just remove everything I'm highlighting right now. So delete all of the text. And in its place, put the symbol on the periodic table that you care about. So if I wanted to look at, say, I don't know, chromium, I would write this in place. Okay? I need to have something there in order to do this example. So I'm just putting it there. So that's the first step. The second step is to figure out its atomic number. The atomic number is always linked to the identity of the atom. So if you wrote chromium, you'd put a number in front of it equal to its Z, which is 24. If you instead did magnesium, you'd put a 12 there. Z is written as a subscript, so it's going to go on the bottom before your symbol. A is going to go as a superscript. You're going to put that above Z. Now, when I have to type this out, I can't actually put a subscript and a superscript directly on top of each other without a special formatting program. So what ends up happening is I get something like this. These two things are functionally equivalent. Okay? So if you see me type ZAE, but the Z and A are not directly on top of each other, that's what I'm intending, is this right here. All right. And there it is. I actually had to do that at the bottom. And then, of course, the last step is to celebrate, because that's what you got to do. Okay? So this right here, this thing that you wrote, is called isotopic notation. Your textbook online might call it complete chemical symbol notation or complete isotopic notation. They all mean more or less the same thing. What is an isotope? We'll talk about that later today. But this is the notation for identifying isotopes. So we're going to construct a bunch of these based on descriptions for elements that we have. So here's an example. Let's suppose I have sulfur. So I wrote its symbol S up here. And I have 16 protons and 17 neutrons. What do I write for Z? What do I write for S? Tell me in the chat, Z equals blank, S, or not S, A equals blank. And I'll put those numbers in the appropriate spot, and we'll see if you get it right. And yes, this is easier than you think it is. Don't overthink it. There you go. Z is 16, A is 33. Very good. All right, I got a bunch of them for you. So now what I want you to do is I want you to write the isotopic notation for each of these atoms that are shown here. Now you're going to notice that I've made some of them into a puzzle, and I've tried to twist and scramble all of the different terms that we've used. So be really careful about what the problem is asking you to do, and then write out the isotopic notation symbol on a sheet of paper or somewhere. Obviously, you're going to need a periodic table to do this, so grab the one from P-table. I'll put that in the chat just in case you didn't bookmark the link here. There it is. And we'll go over the answers in a few minutes. See you then. Sorry, give me just a second. We'll go over the answers. All right, let's go over the answers over here. That's not what I wanted to do. What am I clicking on? Oh, there we go. That was the window capture from the PDF yesterday. So we'll do that. All right, so the first problem we want to look at in atom. Oh, what are lanthanoids? Lanthanoids are the first row at the bottom of the periodic table. So they're the top of the two bottom rows down there. They are called lanthanoids because they start, the first element that starts that row is lanthanum. What they are is, that's a really long question to answer because I'm technically an expert on lanthanoids. I did undergraduate research in a lanthanoid lab. You can send me an email and I can answer that in more detail. I think if I start talking about lanthanoids, I will go forever. What do we got here? I got 25 protons, so Z is 25. I got 27 neutrons. Now, resist the temptation to do that because that's wrong. You don't want to just put a 27 up there. You want to add those numbers together. What's 25 plus 27? I hope it's 52. Otherwise, I'm in trouble because I can't do math. Now I gotta look up what element 25 is. That's manganese. Its symbol is Mn. And you're all set. So that was number 1. That was supposed to be a 2. It just sort of wasn't meant to be there. There we go. An atom with Z equals 37 and A equals 72. This has already been done for us. Because remember, these symbols represent Z and A. What is 37? That's rubidium. So we'll do that. There you go. An atom where the same number of protons and neutrons where A equals 36. Okay. So if there's the same number of protons and neutrons, what that tells us is that whatever the number of protons is plus the number of neutrons, they're the same number. It must be 36, right? What the heck? We're using algebra? Huh? Yeah, this is how you solve that. So if you know the number of protons and the number of neutrons, now you can make its symbol. So Z is 18. A is 36 because the problem told us. And element 18, this should be argon, right? Yeah. There you go. All right. Number 4, also algebra. Yeah, you got to put some algebra in here. So I'm going to call... We'll do Z this time. So Z is the number of protons. And there's one fewer neutron than protons. So what that means is that if this is the number of protons and then this is the number of neutrons, it would be this, right? And that's going to equal the mass number 19. So we'll take that. Z is 10. A is 19 because that's what it just told us. And then where is element 10? That's neon. There you go. So yeah, I can basically turn these problems into algebra problems, which is more or less the only way to make them exciting and not just ask you the same iterations of the top 2 problems over and over and over. That said, I know on the worksheet for Chapter 7, if you downloaded it early, one of my versions of these problems was impossible because it led you to get a fractional result. I've since updated that, but if you don't have revision 2 of Worksheet 7, go ahead and grab it from the webpage. And there should be a key available because that was when I discovered that. All right, let's keep going. We're going to talk a little bit about ions today, just so we have an understanding of how we get them and how they interact with their matter and what we can write for them. Okay. Now, we said earlier that opposite charges will attract each other and like charges repel. That's going to be the basis behind how ions function. Okay, so this is going to be entirely the why behind why any of this happens. In fact, that highlighted sentence right there might just be the entire premise behind chemistry itself. Chemistry is all about charges. What do charges do when they are in close proximity to each other? And the answer is chemistry. Because there are all sorts of gradients of charge. You can have positive charges and negative charges, but you can also have a partially positive charge, because that positive charge is spread out over a bunch of neutral stuff. And so it's a little less intense. And then you have like a balance. Well, okay, I have something that's really negative and something that's sort of negative. What will this positive thing do? And it will most of the time go towards the really negative thing. And that's where all the interesting chemistry stuff comes in. So charge is actually super important. And all of chemistry results from that and the movement of charge. So that what that means is that electrons are going to be the most important thing that we talk about. And thus, learning about ions is really important. So, let's talk about why ions don't just decide to collapse into the center. And that's sort of simplified right here. They move really fast. So, let's go back over here. We'll just scroll this off the screen here. And what I'm going to draw is here's my nucleus right here. And here's my electron. There is a force pulling these two together. And so the electron should just follow the red line. But because electrons are so light, they tend to go... Actually, let me not do that. They tend to move really, 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 really fast. Any object with a momentum will travel in a straight line until either a force acts on it or that it collides into something and then a force acts on it. So, forces are required in order for momentum to change their direction. Well, I have a force here. That's this attractive force due to electrostatics. So what ends up happening is that these two combine, and I end up getting this as my result. And this is what my electron tends to do. Now, this is a little bit oversimplified, but we're going to look at this as a model. I'm going to draw something else that's very similar here. There's the sun. And here is Earth. We'll draw... There we go. That's supposed to be North America. We'll put England over here as just a little bloop because nobody cares about it. And for the same reason that the electron is drawn to the nucleus and the Earth is drawn to the sun due to gravity, so this happens and the sun wants to kill us, our planet should just get sucked into the sun. But why doesn't it do that? Well, it doesn't do that because it has a momentum. It's going in a direction. And the overall result that we observe is this. This is our orbit. Hey, it's not a very good globe, okay? In the same way, electrons orbit the nucleus. However, there is a sort of catch for our electrons. Now, in our solar system, the planets are so far apart that if I have another planet near, even relatively close by, it's not going to have the gravitational influence of the sun, right? Over here, let's say that here's Jupiter. He's way over here in the corner. Jupiter has an influence on other planets, and it will slowly pull any two bodies together, right? But that influence is dwarfed by the attraction of the Earth to the sun. Now, let's suppose that over here, I have... Actually, let me just clear this real quick, because I'm going to need this space here. So let's suppose that I have another atom. So I have another atom right here, and here's my electron, and it's going like this in a normal, regular way. And then it sees this guy right here. If I could play the Metal Gear Solid sound, I would. What do these two things do? Well, they want to repel, right? They don't want to be next to other electrons. And so what ends up happening is that the combination of the attraction to the nucleus, the momentum of the electron, and the repulsion of other electrons leads our electrons to not have orbits that go in a circle. Instead, their orbits are kind of like this. And you can see that there's absolutely no rhyme or reason into which I'm drawing these patterns. In fact, maybe the electron goes over there for a bit. So in reality, the path of an electron is all over the frickin' place. Because there are so many other electrons nearby, there are so many other protons nearby, there are so many other atoms nearby, there are just a ton of forces acting on these electrons in all different directions that we end up with this chaotic pattern that we can't call an orbit anymore, because an orbit is a regular thing that goes around and around and around, right? Instead, what we call this is an orbital. You're going to see the term orbital in Chem 161, and this is going to be the start of quantum mechanics, which is everyone's favorite subject, and by favorite I mean hated. Everybody hates it. For the purposes of this class, we're going to treat electrons as if they just kind of spin around and who cares, sort of like this. But in reality, they go wherever they want to, and we just assume that they are in this region because, as you can see, there's the most red in this region that I'm shading over. So I'm most likely to find the electron here. And that's what the electron cloud is. The electron cloud is just the region in which you'll find electrons. And they move so fast and go all over the place that they don't get sucked into the nucleus. Because they just have too much momentum. They just sail right past it and keep going. All right. The rest of this slide is just review, so we know what both of these say. But remember that there will always be the same number of electrons as protons in a neutral atom. And that the neutrons hold protons together. And you more or less have the entire structure. The why behind how the atomic structure persists has to do with how electron momentum goes. Alright, let's talk about some examples of ions here. The first example of an ion that I'm going to look at is called an anion. An anion, I don't know why it keeps tapping the screen here. An anion has more electrons than protons. Where are my pictures with this? Oh, that must be on a later slide. Alright. A cation has fewer electrons than protons. And then the way that I remember this... And yeah, that's actually where the terms anode and cathode come from. If I were to write the word cation, the letter T looks like a positive. And so you know that the cation is the one with the positive. And the anion is the other one. The other way to remember it, and I don't know if Mito is still here, but Steve likes to do this one, which is cats have paws, positive. And you can't see it, but I'm doing the happy lucky cat thing, where you have the lucky cat statue and one of its paws like goes up and down. I'm doing that right now. And you have to do it in that voice too. Positive. Just Monokiniko. Yeah, that's what it's called. All right. Now, when you are doing the counting for how many protons and electrons there are in something, what you're actually doing to figure out charge is you are taking away negative numbers. So, for instance, if I were to remove an electron, I would be removing something that was negative, and when you subtract a negative number, it becomes positive. So if I say, what's the charge on an atom with 3 electrons and 3 protons, you'd say 0 because they're the same. If I said 3 electrons and 2 protons, that would be, oh, I added an electron to an atom with 2 protons. It would have a charge of -1. If I did it the other way, oh, I'm going to take away an electron, then I would have 1 fewer electron, and then I would have a charge of +1. We're not going to really do redox. That'll become 163. That's when we'll get into batteries in more detail. The general formula that you can use to figure out charge is number of protons minus the number of electrons. And you can think of this as just, oh, well, if I add the number of negative charges I have, so if I have 10 protons, I'd be, okay, there's what 10 protons is, and I have 11 electrons. Protons minus electrons gives us the charge. Oh, here's where my pictures are. Okay, so let's do some examples of this. When I remove an atom, or when I remove an electron from sodium, I'm going to make an ion. Will it be a cation or an anion, and how many electrons will be present? Well, first of all, let's look at sodium on the periodic table. Sodium has this for its symbol. We aren't talking about neutrons, so I don't really know what's going to go here in this space for the mass number, but that's okay. Here's how many protons and electrons it has. I'm going to remove an electron from sodium according to this. So let me change the color here. So I'm going to remove an electron. So I no longer have 11, I now have 10. And now I'll do the subtraction. 11 minus 10 is positive 1. So the charge on this will be plus 1. It's a cation. We don't know what valence electrons are yet, so we'll skip over that until chapter 8. Or 9 or something. What is that going to look like in terms of a picture? That's going to look like this. Here's my electron cloud. One of my electrons is removed. There are less electrons, so it gets thinner. And then I have the sodium plus ion. Now, when I'm counting charge, I write it like this. But if I am showing charge, we show it like this. You put the number, then the charge. And if there's only one, you omit it. So Na plus has a charge of plus 1. When you're writing it on paper, or if you were putting it on like a canvas thing, and I ask you for the charge, always put the number first and then the symbol. If the charge has a magnitude of 1, don't include the 1. Just put the symbol. Let's do the same thing down here. What ion forms when an atom... I can't read today. What ion forms when an electron is added to chlorine? What do you get? So, let's do the same analysis. I got chlorine. There it is on the periodic table. It must have the same number of protons and electrons. And I'm going to add an electron. So instead of 17, I have 18. Now I'll subtract them. 17 minus 18 is negative 1. This will have a negative 1 charge, which makes it an anion, and that'll look like this. Got my chlorine atom. I'm going to give it an extra electron. Oh, excuse me. And then the number of electrons increases, so that region goes whoop, and expands. So as you add electrons, the electron cloud grows. And as you remove electrons, the electron cloud shrinks. There is more to it than that. There are more details. We're going to save that for quantum mechanics. But suffice it to say, the size of the electron cloud is proportional to how many electrons live there. The nucleus will always be the same size, and in all of these pictures, it is super exaggerated. And again, write your charges like that as superscripts. We're going to talk about why this happens in the next section or two. But whenever you have an ionic form of matter and you compare it to the neutral form of the matter, so in this case we're looking at sodium and sodium plus. These are very different. Sodium metal, which is atomic sodium, will explode if you put it in water. Sodium ion is delicious. This isn't table salt. So here's an example. Which form of potassium is in a banana? Is it atomic potassium or ionic potassium, based on what you might have seen in a video earlier on this quarter. Not about bananas, but about potassium. Yeah, it's got to be ionic, right? Because if it was atomic, the second the potassium got into the banana and hit a water molecule, it would explode, right? And that would make eating bananas extremely dangerous, or maybe fun. My cat has decided that it is fun. Kresnik, what do you want? No, do not jump on top of that. Kresnik, come here. He's so lonely, you guys. Meow. Yeah, I know. Adult Pop Rocks, yes. That's exactly what would happen. I mean, losing 1 or 2 electrons not going to be bad for your tongue, but if you had a chunk of sodium, you just burn it. You'd probably burn a hole in it. All right, let's make some ions using these descriptions. So let's suppose that I add 3 electrons to nitrogen. What I want you to do is, in the chat, type in the number of protons and electrons that ion would have. Tell me its charge. And then I'll write all that out on the screen. So go ahead and do that while I tend to what my cat is doing. Because now he's in the corner rubbing a box, and I'm concerned. All right, I'm back. Sorry, I had to... Apparently it was time to hug the cat. He's back for more hugs. What do you want? Well, I know what you want. You want more hugs. You know that's what the cats want when you pick them up and hug them, and they're already purring by the time that you hug them. All right, let's write all that on the screen here. So for a nitrogen atom, I would have 7 protons because its atomic number is 7. I'm going to add 3 electrons to it. So neutral, it would have 7. Adding 3 electrons means it would have 10. And then I just subtract those. And so that's its charge. I think unknown means not observed, or just like no data is available. So like obviously there must be some phase, but that experiment just hasn't been done yet. So if this is the charge on my nitrogen, what I would write for my atom is N, and I put the number first, and then I put the sign. So there's my ion. All right, let me put this one up here. What ion forms when 2 electrons are removed from a calcium atom? So go ahead and do the same analysis. Tell me what Z is. Tell me what the number of electrons is. Tell me what the charge is. I'll give you a second to do that. I'm actually sitting here playing with the temperature slider on p-table now, and so any of the atoms that are gray, yeah, that data doesn't exist for them, and the reason for that is because, for the most part, those atoms are radioactive. And so heating them up that high promotes that radioactivity, and so those atoms just aren't stable at that temperature for long enough to observe a state. So hopefully that answers that question. All right, so let's do the same analysis here. We got calcium. Calcium has 20 protons. It has 20 electrons, but I'm going to remove 2 of them. 20 minus 2 is 18. And then I subtract. I get positive 2. So this would be calcium with a 2 plus charge. There you go. Now let's do it from the other direction. How many protons and electrons does this atom have? Not atom, I'm sorry, this ion have. So you got to look it up. Where's Fe on the periodic table? In fact, I have practice problems coming up in the... Yeah, I do. Here. So, where is my cursor? There it is. So, I'll just do this one real quick. So, this is 26 protons. It would have 26 electrons, but the number of electrons it has leads to a charge of positive 2. And since I'm subtracting, this must be 24. So you can do these sorts of analyses to determine the answers. All right. The most common way you're going to see these types of problems is in this giant table, like this on the next page. So what I want you to do is fill in this table. There isn't a second table. Okay, cool. Fill in this table. What I want you to do is draw the isotopic notation on your paper, count the number of protons, the number of neutrons, and the number of electrons for each species. And you want the entire row to be consistent with all the other information that's already there. Okay? So fill in these tables. Then when I come back, I will go over the answers with you, and then we'll call it a day because we're far enough through Chapter 7, I think. And also because there's only 10 minutes left. So see you in a bit. I realize this one might be difficult to type in the chat, so when you're finished, just say, like, all set or something in the chat. Just to let me know. Oh, that was Steve. Sorry. All right, let's go over the answers here. I'm going to just draw them directly into the table. Let's do red. Here we go. Okay. So I got titanium here. Looking at the periodic table, its symbol is Ti. Looking at its atomic number, it's 22. And then for A, I would need to know the number of protons and neutrons. Well, I got other information over here. So number of protons must be equal to Z, so that's 22. The mass number A that goes in the space would be these two added together, protons plus neutrons. So 22 plus 24 is 46. And then the last thing that we got to do is, it says up here, include the charge on the isotopic notation symbol. So I want to include the charge here. I got 22 protons and 20 electrons. 22 minus 20 is positive 2, so I would do that. All right, let's go to the next one. So what is Br? If you look it up on the periodic table, that's bromine. How many protons does bromine have? Well, it's right here. It's 35. And if my bromine had a charge of -2, how many electrons must be present? Well, 35 minus something must be -2. So the number of electrons must be 37. Or there's just 2 more electrons than protons. For the third one, I got something with 6 protons, 7 neutrons, and 8 electrons. Okay. Well, if it's got 6 protons, it must be carbon. Z is 6, I'd put that there. If the number of neutrons is 7, then A is 6 plus 7, or 13. And the charge is protons minus electrons. 6 minus 8 is -2. You can do the same thing down here with lead. Here's Z, 82. A is the protons plus neutrons, so this number plus whatever goes here is 205. That looks like that's going to be 123. And then for the charge, 82 minus the number of electrons is going to be positive 4. So that means that this must be 78. You can do the same thing down here. You just got to add in the name as well. Number of protons is Z. That's an easy one. Number of neutrons is Z plus, or is protons plus neutrons. So if I add these two numbers together, I get 94. And then finally, to get a charge of positive 3, I need to have 3 fewer electrons than protons. 44 minus 41 is 3. There you go. There's the complete table. And I believe that's all we have time for today. So if there's any last-minute questions, let me know in the chat. Otherwise, I have a few last-minute announcements to make. So lab number 2 is due next Thursday, not today. I just got an email about it. I was like, oh, no, that's not due today. I have not put the assignment up there yet. I will do that immediately after class, after I use the restroom. The other thing I need to do is I need to open quiz 3 because I made it and I don't think I published it. I don't think I hit the button. So if you could see it, that's great. It's supposed to be there. But if you're like, oh, where is quiz 3? I don't know. That's my fault. I'll fix that. So those two things are coming up. Next week is the last week before the midterm. The midterm is on Monday of week 6. And yeah, you will have a quiz on that week too before the midterm. And it will be due slightly earlier so that I can release the key so that you can use it to study. Okay? So next week's quiz, I don't know what the quiz is going to be on. Which chapters is it? Is it 7 and 8 or did I split these up? I have a piece of paper somewhere that tells me this in my lab notes. There we go. Yeah, the next quiz is 7 and 8 together. So next week there will be a chapter or a unit 7-8 quiz that'll probably be due Friday. And then have a hard deadline of Saturday. The key will be revealed after that hard deadline, and that hard deadline will be in the middle of the day. So you have Saturday night and Sunday night to use those quizzes to study for the exam. Okay. The exam will be on Monday during week 6. And there will be a notice down at the bottom. I have this little thing. Let me see here. I have this. Boop, boop. That I put on there. It won't blink. And it'll say exam on Monday or something like that. Just to remind you that, like, hey, exam's coming up. Don't miss that. Because if you don't take the exam and you don't tell me a good reason why, you're pretty much hosed. Like, you can't pass the class. Okay? I think that those are all the announcements. So, if you need anything this weekend, please be sure to let me know. More than happy to help. Have a wonderful weekend. Stay safe, stay healthy, stay at home.